Hello, everybody. I'm super excited that all of you could make it to this Code Labs Tech Talk. Today, we're going to be hearing from Michael, who has 8 years of experience as a software developer. And just a reminder, you can ask questions throughout, and we will address them as we go. We will also have a recording of this talk on our YouTube channel in case you want to rewatch it. And we're also streaming on Twitch, and I'll be monitoring the questions there as well. Thank you.
Hello. I hope everyone's doing well today. My name is Michael Kalish. Today we are going to talk a little bit about an introduction to containerized software development, and we're going to be exploring the history of virtualization. All right. So the goal here is we want to provide a high-level overview of a technology that has really sort of grabbed the industry. It's sort of most famously version is this buzzword is Docker. And so today we'll talk about a little bit of the industry pressures that led to containers becoming so prevalent in a software developer's life. The way we're going to go about that is we're going to go walk way back in time and talk about how the last 60 years of work really enabled Docker to become an important part of our tool set today. All right, so introductions. Like I said, my name is Michael Kalish. I've been a programmer for the last 8 years, and I've had a chance to work on with a bunch of different companies, a bunch of talented people, and a bunch of cool products. Currently, I'm a lead engineer at a company called Curiosity Media, and we're the team behind products like Spanish Dict and Fluencia. And I have a link to my GitHub account if anyone wants to check it out after the slides get shared. There I am on the right with my wife. That is actually us on our honeymoon in Japan. And I also, we have a puppy named Jessie, which I included because I always know that people love puppy pictures. All right, so what are we going to talk about today? All right, so first off, we're going to start where we are today. All right, then we're going to walk back a whole bunch of years, and we're going to talk about where we were. We'll talk about the history and evolution of virtualization, and then we'll ultimately get to the point where we'll talk about what problem did containers and Docker solve for the industry. All right, so this is a little word cloud of just technology choices available to a developer in 2020. I don't know quite how accurate this is in terms of the size of the words, but I put it here just to sort of give a sense of sort of the vast variety of choices that faces a developer. All of these languages have their own pros and cons. They all do different things better. But more importantly, they all exist in the wild, and they're all things that a developer might encounter. All right, so it's great. I love it. There's always new things to learn. The downside of this is that there's always more and more ways for things to go wrong, the more variations and permutations we have. So this is where we are today. A huge amount of flexibility in the tools we implement, but then also the downside of having to manage all these tools. All right, so now the part where we go back in time. I want to pause here real quick and just to reconfirm, please, if you have any questions at any point, we're going to look at a couple diagrams that might be slightly confusing. Please, if at any point you have any questions, just please ask and we can talk about it. All right. So first, we're going to go all the way back in time to before 1963. All right. In 1963, there's a little company called IBM. I don't know, maybe you've heard of them. But when it came to computers, they were really the only option in town. And the way it worked is you would go into IBM and you would say, I would like to rent your computer. They would say, cool, here's your computer. And you'd walk in, you would feed your program into one side, you'd walk all the way around, and then outside the other end would print the results of your program. So it was one way flow, and it worked great because that's how people thought computers were supposed to work. And this sort of flow is sort of like the most basic idea of how a computer might work. And I have it represented here in what is called like a Turing machine or a Turing diagram. You don't really need to understand all the letters or the arrows, but the important thing to notice here is sort of this one-way flow. Ultimately, you start in A. It's the only place you can start. And eventually, if you follow all the arrows, you always end up in H eventually. And that's how IBM machines worked. And it was great. And it was sort of all the rage up to 1963. All right. So what happens in 1963? All right. So 1963, interestingly enough, was also the first year the Beatles released, the first year that the Beatles named themselves the Beatles in the US, and they released an album. What also happened in 1963 is that MIT was still one of the leading technology researcher and academics, and they won a grant from DARPA, which stands for the Defense Advanced Research Projects Agency. These guys pop up everywhere, and they are a pretty famous group. I think they appear a bunch of times in sort of pop culture references, but what they're typically most famous for is they're attributed with being a large part of the invention of the internet. But that's another story. All right, but so for today, 1963, DARPA gives MIT a grant, a $2 million grant. In today's money, that's about $16 or so million, give or take a few. All right, this grant was for research into operating systems, artificial intelligence, and computational theory. So a lot of meaty things and stuff that honestly we're still researching today. These are all sort of words that you could see in academic papers published in 2020. And so the theory behind these is still sort of works the same way. Anyway, so as part of this process, MIT wants some new computers. They put out a bid, and what they want is someone to build a computer that has the capability of running multiple programs and also accepting user interaction. So they put out a whole bunch of bids, and they go after IBM. They put out bids to other people. They also put out a bid to a company like GE. So they put all these bids, and of course, the bid ends up going to GE. So I would not say that most people typically associate GE as on the forefront of computational academics. But what happened at the time was when MIT went to IBM and said, we have this new machine we'd like you to build for us in order to run our new experience. IBM told them, no thanks. We like our system the way it is. It works great. It works perfect. And besides, no one would ever want to buy such a thing. Who would ever need a computer that accepts multiple users at the same time or multiple processes? So this is still 1963. So they say no. MIT says, fine. If you don't want to build it, you don't want to build it. They give the grant to GE. All right, so we fast forward a little bit some more. Ultimately, GE doesn't really do that much with it. All right, so let's go forward 5 more years. All right, the year is now 1968. So other things that happened in 1968, just to sort of tie it all together, at the same time we're having these conversations about computers that can only support one user. In 1968, Apollo 8 was the first mission that successfully sent an American astronaut around the moon. And this is a little picture of the Apollo 8. All right, so what else happens in 1968? So this is 5 years after MIT first wanted to have a computer that was capable of doing this, having multiple users and having user interactions. And as it turns out, this is actually something that people did want. It's very, very useful and far more convenient than sort of IBM machines. So 5 years after IBM had a chance to build the first one, they realized that this is a wake-up call and maybe it really is time to build one. All right. So 1968 is the very first rendition of this diagram below, which we'll talk about in a second. And then it took another 4 years, not until 1972, for IBM to make this commercially viable and actually be able to sell it to outside of academics and to the government. So let's talk a little bit about this diagram that we see here. So on the outside, we have a whole bunch of users. We don't know what they're doing. They might be real people. They might be a mouse. They might be a keyboard. But the thing of it as some sort of user performing some sort of action and then wanting to see what happened and having hardware perform that action for you. Everything inside of the black circle with the little CPU in there is physical resources. And by physical, we're talking about stuff like hardware, RAM, CPU. This is actually something that would have been plugged in, electricity runs through it. So the big idea here was, all right, So we have a set of resources, and currently the way it works is at one time, those resources can be dedicated only to one process, a la the IBM method of Turing machine, one-way flow. The inspiration was, all right, well, what if we just shared those resources and each user could take a turn? So currently user 5 has all the CPU and hardware, gets to perform a couple calculations, it gets paused for a second, the error moves to user 6. User 6 says, all right, I'm going to take some time. I get to run a couple of calculations. User 6's time is up, goes to user 1, and so on and so forth. And so to the outside of the system, it looks like a bunch of things are going on at the same time. But in reality, the system is just sort of delegating time slots to all these different processes. All right. So but the important concept here is the idea that in 1972, we sort of formalized the idea of sharing resources and sort of presenting a virtualized version to the user of what was available to them. All right. Also happening in 1972, something called Unix became invented. Unix is pretty famous now. Lots of modern operating systems were derived from Unix. But sort of the first sort of named rendition came out in 1972. And in fact, it was heavily driven by the work that IBM did with that time sharing. So what was sort of the idea here? Unix took that idea of virtualizing resources and abstracted it even further. If we're going to say, all right, users, you're all going to take turns and you get your own sort of reserved space of hardware and resources memory, why can't we also do that on a sort of a more abstract layer for something like folders, documents, and text files? And thus, Unix was born. And it was the concept that we would want to perform virtualization on the user level. Jumping forward another couple of decades. So we're now in 1994. This is a little, and interestingly, what happened in 1994, Linux 1.0.0 came out. So the very first version of Linux. It's one of the most famous operating systems. I'm going to pause you real quick. So virtualization of resources. Let me go back to 2 slides. Here we go. All right, so when we talk about this slide, we were talking about how let's use our example for user 5 who actively is using the resources. So user 5, to them, they think they have the full set of RAM and they can use it, the full set of hard drive space and memory, and they have all of it, it's theirs. Well, in reality, the underlying system is actually providing a virtualized view, because in reality, user 5 doesn't have full-time access to all that hardware, all that memory, and all that CPU. They, in fact, only have a sliver of it. But from the perspective, they have the whole thing. So the idea of virtualization is that you have an underlying system that makes it think that the virtual system has all of the resources available to it. Feel free to follow up if that doesn't answer your question, since I cannot tell. But please just ask another one if that didn't make sense. And then we can also, I'll have some time at the end and we can revisit anything that didn't make sense. But the key here is that virtualization is the idea that you want to convince user 5 in this slide. The follow-up question, is this like how cores work on a CPU? Yes, it is very similar to that. So, so a CPU has somewhere between, a lot of modern CPUs have 4. And so when a process starts running, they might be told, we're only giving you access to 1 core of that CPU. And but from their perspective, there is only 1 core. So they have a virtualized view of how many CPU cores are on the CPU. All right, so let's continue forward. But yeah, so the key here, I think everyone's sort of picking up on the idea that there are some resources like CPU, cores on a CPU, RAM, memory, and they are finite. And then the idea of virtualization is to make sure that is to have lots of different processes share those resources, and we do that by virtualizing how much resources are available to them. All right, so let's keep going. All right, so we talked about 1994. Linux just came out. And so we went a bunch of years into the future here. So things were pretty good. So, and the status quo, it really just worked for a while. But there were still, a couple problems that people still faced. And I think one of the problems was the reality was that software was still not that portable. Something even as simple as folders would need to be implemented specially for each operating system. This was a process known as compiling. So I have this is a little engineer humor for you. So compiling takes a long time on some of these older systems. And while it's compiling, there's actually no work to really be done back in the day. And then the reality was, as we got more and more operating systems on the market, so let's think it's 1994, we now have Windows, we have Mac, we just saw Linux, there's a couple other operating systems that have just sort of died out. And if you wanted to have folders, you sort of had to write a separate folders app for each operating system. And that was really annoying. Folders are sort of simple and they generally work the same way. It's a nice abstraction. Why should we have to write the same abstraction over and over again for each operating system? All right, so a company called Sun, they no longer exist anymore, thought to themselves, all right, we think we can do better than that. I think we can make software more portable. So what do they invent? They invent something called the Java virtual machine. And I think it's probably something that's a lot of people might be familiar with, if not just with Java, that's sort of the term. So what the Java virtual machine did is it served as an intermediary between the application and the operating system. So if you remember what we just talked about, we had all these developers who had to write essentially a custom application for each operating system. It's expensive, this compiling took time, it was error prone. And so what the problem that was solved here is that your customer could install Java, and then you would only have to build one application against the Java virtual machine, and it could run anywhere. This is how we got to the point that pretty much every computer on the market these days comes bundled with Java. It was an incredibly convenient virtualization technique so that a developer could write one copy of the code and then have that code run the exact same way across a whole bunch of different operating systems, rather than being responsible for handling all the intricacies for how they work. So a good example is that the Windows operating system works very, very differently than the Mac OS operating system. And then sort of like for anyone who might have ever installed Java, sort of the prevalence in the 90s, they also had a little bit of idea that the internet might be coming, which also sort of drove this concept. But they coined sort of the famous term, every time you install something, Java runs on 3 billion devices. But it's true, in the 90s, Java was revolutionary. This was a concept that sped up development and really sort of codified and eliminated a layer into an abstraction so that a developer wouldn't have to think about it anymore. So a good way to think about it is, as we're adding new technologies, we're increasing the abstraction layer so that a developer, rather than thinking about how do I implement folders, can think about cool things of, how can I implement something like Twitter? All right, so question. So does this mean that most code was written in Java during this time? Lots of code was written in Java at this time. And in fact, lots of code is still written in Java at this time. And 1994 is now a very long time ago. And it's not the same version of Java. They've slowly iterated. But yes, lots and lots of companies still use Java to this day. And it's still vastly popular. Even just in my 8 years, I've worked on multiple Java applications. So it's something that's still extremely common to this day. And so it's sort of nice to know the history. So, and then the other side of this, there were other competitors, but Microsoft also had an offering for anyone who might have heard of like .NET. But the concepts were sort of similar, but I would say that Java had at least some very large prevalence, partially due to sort of its open source, being an open source project in many ways. And for anyone who's curious, I mentioned that Sun was the company that originally came up with the idea. These days, the Java name is owned by a company called Oracle. All right. So let's jump a little further in time, unless anyone had any other questions on Java or the JVM. All right, so 2001, we're getting a little closer to today. All right, so we've talked a lot about how on the application side, so folders, websites, browsers, word processors, developers were working very hard to sort of make it easier to make this software more and more portable. So at the same time, operating system developers were trying to do the same thing and make operating systems more portable. Right? What does that mean to make an operating system portable? All right. So the diagram I have up is something called a hypervisor. In 2001, they're still a very large company today. The main player in sort of this operating system portability or virtualization was known as VMware. And these were the two products they offered. It was the Type 1 hypervisor and the Type 2 hosted hypervisor. Sort of fancy names. But these diagrams are actually really good ways to sort of explain what was going on here. So despite there being two diagrams, they sort of end up working the same way. So on the far left, we have our server and hardware. And once again, these are physical machines. They are plugged in. They actually have hard drives that you pull in and out. They can break. They have RAM. And so that's on the far left. And this is very similar to what we talked about all the way back up when we show that time sharing diagram. Same kind of physical resources. That has not changed. What has changed is what comes next. So the top and the bottom differ in one subtle way. On the top diagram, we have the host operating system in there. That ends up being more sort of implementation details. But the important part to notice here is that we have a new player between our hardware and then what is on the far right, which is operating systems. So the top one could be a Windows machine, the bottom one could be iPad, Mac OS, and the bottom one could be Android, all different operating systems. What happens here is the hypervisor is then responsible for translating or distributing the resources on the server hardware to all these virtual operating systems on the right. And so this was the technology that was available. So what this enabled companies to do is I could buy one really large server hardware. I'm talking, we're 2001, so there weren't that many things, but I'm talking, 2 or 3 terabytes, maybe, 120 gigabytes of RAM, beefy machines. I can install one copy of hypervisor, and then I could actually have a whole bunch of other machines running. And this was great because by 2001, applications were complicated. An application might have some sort of web server that was responsible for communicating with a browser. It might have a database that is used for storing records, and then it has to talk to the internet. So all of these things are very complicated, and it was far cheaper rather than having to buy a physical server per machine you wanted to run. VMware, with their hypervisor technology, enabled you to buy one server, which they can run all of these resources at the same time. All right, so I just wanted to pause here because this gets a little complicated and a little technical. See if anyone had any sort of questions here. But the key point is the hypervisor sits in between our physical hardware and our virtualized operating systems and is responsible for making sure that each virtual operating system has memory when it needs to and doesn't know that it is a virtual operating system. All right, so let's move on. All right, so we'll go forward one more year, and this is 2002. So what we can see here, I used if you haven't seen it before, there's a program called the Wayback Machine, and so this isn't actually what Amazon looked like in 2002. You can sort of see the outline from the Wayback Machine, and so looks actually sort of similar to what it does today. But even in 2002, Amazon had sort of become a major player in the sort of the online shopping market. All right, so 2002, Amazon is really sort of accelerating, becoming incredibly successful. We go to 2006, where a problem becomes a solution and the cloud is born. All right, so I have a little funny picture here. Brace yourselves, the Christmas rush is coming. I don't know about all of you. I tend to heavily use Amazon to purchase my Christmas gifts or Hanukkah gifts around the holiday season, and it's incredibly convenient. But the reality of the problem they face is that in the months of November and through, midway through December, the peak of the number of customers that Amazon had to serve was incredibly high. Everyone was buying their Christmas gifts and Hanukkah gifts and holiday gifts all at the same time. However, you hit March, traffic is way, 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 way lower, and you need and you don't need to serve nearly as many customers. So the problem that Amazon was facing was that in order to serve their holiday rush customers, they had to pay for lots of physical machines. They needed a lot of hard drive space. They needed a lot of RAM. They needed lots of CPUs. They needed CPUs with lots of cores in order to serve all that. And then come March, all that hardware sort of just sat around. They're paying for it. They're paying for it, the electricity, the cooling, but it doesn't really go unused. All right, so a bunch of smart people in Amazon, they're sitting around. What are we going to do about this problem? All right, we're going to sell it. That was the idea. And thus, Amazon Web Services was born. So Amazon was going to go ahead and all this infrastructure and machines and hardware and electricity they were already paying for, they were just going to say, if you want, you can rent it for us. If we notice, there's a similar pattern here with sort of companies renting computer time. So in 2006, this idea became a reality. And in 2006, the first two offerings as part of the sort of AWS Amazon Web Services launch was called okay, this is a good question. All right, why couldn't they just turn off the servers that they weren't using to save costs? All right, so they could do that, and they did do that almost certainly. But there's sort of a reality of a company as big as Amazon, a little bit of an operational inertia. The machines, they don't work like on-off switch. To go back a slide or two, when we're talking about the machines they're not using, we're talking about them on the far right of this chart. So we're talking about a user one Windows machine that maybe that machine powers some sort of internal warehouse application that Amazon uses. And then the user 3 virtual machine is actually powering a website. So it's not always as simple as saying, oh, we'll just turn it on and off. Additionally, there is just the cost of it doesn't happen by itself, that you have to pay someone to go turn it on and off. And hopefully you turn it on at the right time. Or if you don't, you could run the risk that in 2002, just in the middle of this rush, if you didn't turn it on quite at the time, all sorts of users are seeing broken Amazon pages and can't buy anything. So yes, it was always an option to turn it on and off, but the cost of doing that was also quite large at the same time. All right, that was a really good question. So Amazon Web Services is born. They have S3, which stands for Simple Storage Service. This is really just as simple as Amazon was renting hard drive space. And they had another fancy one called EC2, known as Elastic Compute Cloud, which is also just another fancy word where people could go rent virtual computers. So great. So this is an immediate success. And this is really sort of the beginning of the cloud becoming a thing in everyone's head from a software development standpoint. All right, getting a little closer to more modern times. We now hit 2008. Barack Obama is president. And interestingly, also in 2008 was the first year they turned on the Large Hadron Collider, which is what we have on our right. All right. So what else was happening in 2008? JavaScript takes off. All right. So in 2008, the internet is a thing at this point. Everyone knows about it. Everyone uses it. It's in schools. There's laptops. You're really starting to see the beginning of smartphones becoming a thing and people having internet on their phone. I believe the first iPhone was released in 2007. And what was common about all these access points where people were using the internet, everywhere that people were using the internet, JavaScript was installed. So JavaScript, for those that know, is a very popular programming language. This chart only goes up to 2013, but this trend has only continued as we've through 2020. And it's very popular because it runs on every browser and every developer can write code that they know will then run on and work on a user's browser. Just since we're talking about history today, the first browser to implement JavaScript was actually a browser called Netscape, which is very old. But that was the sort of, you're curious about where JavaScript came from, it sort of started all with Netscape. All right, so why am I talking about JavaScript? All right, so because the internet is everywhere, everyone wants to write web apps. I don't want to have to go and mail someone a physical CD so you can install Microsoft Word and copy files over. That's crazy. There's Google Docs. But in 2008, that was less of a thing. But we sort of marked the beginning of every sort of application had some sort of internet browser experience, and all of those experiences, for the most part, were driven by JavaScript. And like, as just an example of a technology that did serve this purpose, but sort of faded out as JavaScript has risen, sort of in the 2008, Flash was everywhere. Flash games. And as of right now, most browsers have disabled Flash by default in favor of running JavaScript. So why are we talking about JavaScript, though, once again? When you think about all the way back to the beginning of these slides, I showed you a word cloud of programming languages. Right? It's a pretty big word cloud, lots of things, lots of languages, and they're all used. With that being said, if I were to show you the word cloud of tools for JavaScript, it would have been an even bigger word cloud. There is many tools, all for doing little different things with JavaScript, all to sort of optimize that browser experience. So if you can imagine, we have that same word cloud, and then it's mixed with an even larger word cloud of sort of these JavaScript tools. So the number of things that a developer needs to know and have installed and working correctly on their machine is very large. And then the number of tools and technologies that are infrastructure out in AWS or out running on physical hardware also needs to have all these tools and stuff installed. And it's a lot. And if they get messed up at any point, the web applications can stop working on the web. So it's a big deal because we have just all these tools and we need people to maintain them. All right. So in 2009, we have our first DevOps conference in Ghent, Belgium. I don't know if I pronounced that right, but I believe so. Just a couple fun facts about Ghent, Belgium, because I didn't know this, and while I was pulling this together, I thought it was interesting. It used to be the second largest city in Europe, second only to Paris, and it was most famous for producing wool. And the little picture here that I have is actually sort of a city-sanctioned graffiti section that Ghent is now more sort of known in a more modern sense. All right, so why am I talking about this weird conference in this weird town with graffiti? All right, DevOps Conference, what does that stand for? It stands for Development Operations Conference. So operations largely means is a job, still exists today, especially at some very large enterprises that have complicated infrastructure, but it was a whole job dedicated to maintaining operating systems, making sure that this computer had enough hard drive, creating new virtual computers, managing databases, and it was a whole job. In fact, whole teams of people were dedicated to just doing this full time. And it was complicated. It was a lot of pieces, there were a lot of commands, and if you ran them wrong, it might not work correctly. So in 2009, they all got together and say, all right, this is a real job. People need to do this. We're going to start talking about what are like good ways to do this that are repeatable and that they work the same way every single time. And like, how can we say, application developers for years have been writing down their code and then saving it in places. Can we maybe do the same thing with some of this maintenance of operating systems, updating packages that need for security updates? So it was sort of the beginning of this movement of, yes, this is a possible thing. All right, so let's fast forward a couple more years here. Was it 4 or 5 more years later, 2013. Interesting thing that happened in 2013, sort of fun fact, Pope Francis joins Twitter, and unshockingly is the first pope to ever have a Twitter account. What else happened in 2013? 2013, the first version of Docker was released. And that's sort of the beginning of Docker becoming a sort of a very common development tool. All right, so I'm going to pause 1 second right here, see if there are any questions before we go into sort of more a detailed explanation of how Docker works, and sort of in comparison, especially to that diagram I mentioned about with the hypervisor from VMware. Cool. All right. So how it works. On the left, we have what was a typical virtualized guest OS infrastructure system. And this is what AWS, we mentioned that EC2 Elastic Compute Cloud. The diagram on the left is exactly what they offered. I would say I need to run an application, and I would rent from Amazon one of those boxes labeled with guest OS. And it worked great. All right, so, but there's, so this worked really well, but there's one thing that was like a little bit of a problem. So a Windows operating system is big. It needs to do a lot of things. It needs to know how keyboards work. It needs to know how mice work. It needs to know how graphics cards work. Lots of stuff going on there. And there's code that makes all of that works. When you're running a web application, one that might be responsible for looking up something in a database and sending to a browser, the code that runs a graphics card doesn't do anything, and it just takes up space. So what was the solution to this? Let's just get rid of it. On the right, we have sort of a basic diagram of how Docker works. Or the Docker infrastructure works. The first thing we can notice here, it's shorter. There's just less stuff going on. And what we've removed here is the guest OS. So instead of having a host OS, a hypervisor, and then a hypervisor mediating with guest OS, we have just a host OS, what is called the Docker engine. It sort of is the special sauce that powers all this. And then we just have applications running. So we immediately just eliminated a whole row in complication from the diagram here. This meant it was simpler to develop. It meant it was simpler to get the application deployed to somewhere like AWS. And it was simpler to understand when things get wrong. And overall was a little more secure too. All right, so any questions on the hypervisor versus the Docker engine on this diagram here? Great. All right, so continuing down, I promise this is by far the most complicated diagram we have, but I wanted to provide a little bit more insight into what was happening in that Docker engine box, because it's complicated, and in order to make this work, it did require a little bit of a spark of innovation here. All right. Hold on one second. I think I might have a. We have one question about JS tools. Sure. If you want to type it in, or we can come back to it at the end.
Oh, sorry. I think it's in the Q&A box. You may have just missed it.
Oh, did I miss it? Oh, there it is. Yep. All right. So what did you say the solution was to all the JS tools? Oh, if I knew the answer to that, I would be a much happier person. It is still a problem today. It's very exciting because there's so many tools, but there really isn't a solution. These tools weren't just made just for the fun of it. They all serve really important purposes. And it's something actually that the industry is sort of struggling to wrangle with right now of what to do with all these tools out there. But the reason I bring it up is as we sort of talk about Docker, Docker actually sort of helps solve the solution because it allowed us, as you'll see, to not have to remember all the tooling we installed, and we can just write it down and hand that to a developer, and it'll automatically install it all for them. So let's go a little bit further, and then hopefully we can maybe circle back to that if it's still not clear. All right, so what we have here, we have something, it's called our teal box is our Docker host. Our purple box here says volume. You can think of this is just a hard drive. And then our sort of slightly different purple box out here is called a client. It's a web browser. Firefox, Chrome, they're going to make requests to websites. All right. So the interesting bit here is our box called app 1.0. And notice they're stacked very interesting here. We're sort of stacking from, so these terms might not be all available. Everyone might not know these terms, but they stack in sort of order of abstraction. So this first one down here, Debian Jessie, that's just another name for Linux, which is an operating system. All right, next layer up, Python. This is a programming language for anyone who doesn't know. Very popular, people really like it. All right, let's go up one more layer. Django. Django is a application framework that is built upon Python. That is also very popular. It's really easy to get started. It's very popular with a lot of sort of volunteer open source communities just because of sort of the ease of use. On top of that, we have UWSGI. This is not important. But above that, we have Nginx. This is what is called a web server, and it's responsible for taking in requests from a web browser. And then finally, we have the application that you as a developer would be working on. Oops, sorry about that. So the key part here is to think about sort of this, why we're stacking it this way. So at the very top, I have an application. It used to be, in order to run, if I wanted to run my application on my own computer, I'd have to go install Python. I'd have to go install Linux. I'd have to go install Django. And fingers crossed, I install Python 2.7 and not a version of Python 3, because otherwise my application doesn't work. And hopefully I install the right version of Django, because otherwise it might work, only sort of work. Finally, hopefully I remember how to set up a web server, because I don't really set them up that often, and when I do, I always have to go Google it. All right, it's a lot of dependencies, and I have to remember how to do that. And it used to be, if you joined a new company or joined a new open source project, the first thing you do is spending all day making sure you installed all those things correctly. All right, so cool. We talked about what sort of this problem was. The sort of leap of innovation was that we can, once we eliminate having to have this heavy guest operating system with all this other code that we don't really need, a graphics card like we talked about, we have much smaller packages that in order to express our entire application. So the idea was that, all right, how can we minimize the size of our application? So I'm writing my application that we see here, and I need to change a file that Django provides. Doesn't really matter which file, but the point is I only need to change that one file inside my Django yellow box. Before Docker, in order to do that, I'd have to copy the entire version of Django and all the files and make my one edit in that one file. With Docker, I only copy the one file I want to edit, and then I just continue to use the old files because I haven't changed them. So because of that, we're able to scrunch space on each layer we need, because we only add in the files that we need to make our application run, rather than getting the whole kitchen sink. So I apologize, that's quite a bit, and we're getting a little into the sort of the deep dive, but the key point here is that the Docker allowed us to build up infrastructure and dependencies and applications in a memory and space efficient sense. All right, so why does that really matter? All right. So what we have in front of us, this is actually a real Docker file. And inside are our commands. And this Docker file is going to, you're going to execute these commands against a virtual operating system inside the Docker engine to produce our application. So it's a pretty good syntax. It's convenient, it's neat. And if we think back into 2006, these kind of commands, these were hand entered by people, sometimes by memory, and sometimes they were stored in a text file on someone's computer. But the whole point was it was error prone because it was sort of a human was typing it, and it was sort of reliant on a human having the correct memory of how to do it, and nothing had changed. The convenience here is that we can write down all of these commands and we can save this file. And then you can share this file with whoever you want. And if they use this file with Docker, you can guarantee that they're going to get the right version of Python. They're going to get the right version of Django, and everything will work as expected. Why can't you just create a GitHub README page? I think that was the question here. So that was, yes, very popular. And that does work. And I think, that is still what a lot of teams do. I think, but for some of the reasons we're talked about, it solves the writing it down problem. Doesn't solve necessarily the fact that, even when copying, you can miss a character or something can go wrong. or something can change order and you might not know about it. So for a while, GitHub pages were very popular and still are to this day. And then to give like a sort of another example, sometimes when you're working with other stakeholders, they might not be as technical as you. Let's think of sort of like maybe a designer who wants to run the application, but might not be able to run all these commands and know how it works. Docker provided a convenient way to hand over something to our designer, and they can take a look at it. But yes, so for a long time, GitHub README pages were a very popular way to sort of store this information. You still see it to this day. And it's especially still popular with sort of like open source projects that maybe serve more as dependencies and aren't actually fully running applications. And then the flip side of that, sorry, not the flip side, and a sort of follow up to that, this sort of syntax of writing it down. So Docker was not the first technology to sort of do this. There are other ones. There's Chef, Vagrant, Ansible are all sort of industry buzzwords. And they were all sort of premised around the same idea of, all right, it's probably a good idea if we write all these things down and save them somewhere. And if we go back to when we talked about DevOps, these tools were some of the tooling that came out of minds getting together thinking about that. So we talked about the Docker file providing that easy convenience. But on its own, you're probably right. There might be an argument that maybe a GitHub page is easier. Yes, that is correct. So people previously used virtual machines. So we think back to when we showed that VMware Hypervisor 1, Hypervisor 2. That's actually software that you can run on your personal computer and run it in a virtual machine. And so for the longest time, I do a lot of work with sort of volunteer projects. When we onboarded a new volunteer, we had them download a virtual machine and run it that way. Because maybe the volunteer came in with a Windows machine rather than a Mac. I know it works for Mac. I have no idea if all these commands work on a Windows machine. They probably don't. You probably need different commands. However, if we're both using the same virtual machine, same copy of a virtual machine, we know it's going to work the same way. So that's a good way of summarizing it up. So what Docker did is it took that concept, which was great. Here's a little virtual machine. It runs just my application. And it strips out all of the extra stuff that was in that guest OS, which makes it an incredibly tiny little package that we can then distribute to people. I can send it to the internet. I can put it on a USB drive. I can put it on a CD-ROM. Anything you want to do, you can put it in Dropbox. It becomes this very tightly packaged thing that can be exchanged. So what does that end up being? So almost all applications these days need some sort of database. Now, it used to be very complicated. There are a lot of databases, MySQL, Postgres, MariaDB. They all have multiple versions. The versions do different things. And applications are often designed to only work with specific versions of that database. So it used to be a real headache of, all right, so I'm a new developer. My company uses, this is made up numbers, but a real example. My company uses Postgres 8. But when I showed up on day one, I can only find a download for Postgres 10. So that was sort of troublesome. So maybe you'll run Postgres 10, maybe it works, maybe it doesn't. But the point was it wasn't a deterministic thing. You were sort of hoping everything would go okay. The convenience Docker added is, so this is an actual command, an actual Docker command, is I can just say, all right, I want to use MySQL and I want the latest version, Docker pull MySQL. If I wanted to change it, I could also specify which version, Docker pull MySQL, and then say what version you wanted to pull. And in the time it takes to download, generally a pretty small amount of data, you can have a immediately running version of a MySQL database that would take potentially much longer. Additionally, it gives you the option of running multiple versions of MySQL at different versions. And it all sort of is powered by this virtualization layer, but a very tiny virtualization layer. All right, so I'm going to pause here because this sort of ends like the technical portion. And then we just have one more slide talking about sort of what this means to the industry. But if anyone had any other questions on sort of the technology that powers Docker, now would be a good time. All righty, cool. So why is this so awesome? All right, this is really, really, really good for the little guy. Today, lots of companies are using Docker. It's incredibly popular. You still see some of the sort of much larger companies, I'm talking about big banks, insurance companies, they still at times use their own infrastructure, and they sort of don't take advantage of this container service for lots of reasons. Inertia, the cost of switching, the risk of switching. So it all means that these really big companies might not have jumped on the bandwagon. That's okay. This technology hasn't stopped working. But what it does mean is that for these little guys who want to make real rapid prototypes, real rapid forward progress, and go from 0 to 60 really quickly, there's a technology that really speeds up the process. And the other thing that sort of made it a lot easier for sort of little software shops to really reap the benefits of this is that as of a couple of years ago, Amazon actually rolled out sort of their own version of this container technology. They called it Elastic Container Service. And it's a service for running Docker containers or defined by these Docker files like we showed here, and running them on AWS infrastructure where they have their own Docker engine. And then it also allows you to easily integrate with some of the other services that Amazon offers, like the S3 that we mentioned and some of their database offerings. So it made it much easier abstraction for small teams. We mentioned that job like an operations job. That's the kind of job that you can only really afford if you're a much larger company. So for smaller companies, Amazon provided this really easy, convenient way where as a developer, I can hand Amazon my application in this beautiful little container, and I don't have to worry about how they run it. They just stick it on their cloud and it works. So it serves the double purpose of it significantly reduces the cost of maintaining an application. There's less to think about, there are less moving pieces. And it also drastically enables a lot more flexibility for developers. And it makes all these tools a lot simpler to work with because you can have the confidence that if it runs on your local computer, it's going to run the exact same way on Amazon's virtual computers. So it's a huge savings, both in sort of the mental energy for your development team and also just the pure cost of running these applications. All right, so this is the time for any other sort of follow-up questions. I'm done with slides. We have one more here at the bottom. This is just a link to some of the sources I used to pull this talk together. But now, yeah, so that's our intro to containerized development. Just for the sake of full transparency, Docker is a tool that I have used sort of every day as part of my daily software development life cycle. So one more question. So is that called deployment when you push to AWS? Yes, that is commonly what deployment would means. Yeah, so deployment would mean I worked on it on my computer, I packaged up this Docker container because it worked great, and I deploy it by pushing it to AWS. That is absolutely correct. So. All right, any other questions? I'm happy to go back to any other slides if anyone has any curious or wanted to see anything again. And like I said, I think you'll be able to, you'll have access to these slides. All right, I don't know if we have any questions from the Twitch or the Discord channel, but if not, I think this is a good place to wrap.
It doesn't look like we have any more questions.
Okay. What does Docker do to abstract away the hypervisor? Okay, that's a good question. So it's less of a thinking of abstracting the hypervisor and more of thinking we are replacing the hypervisor. So the hypervisor is really good at being in the middle and knowing how to make guest operating or virtual operating systems work. So that's what the hypervisor does. The Docker engine skips that whole guest operating system, virtual operating system entirely, and replaces that hypervisor with what we talked about here in this diagram of sort of collapsing all of our dependencies into one container. Good question.
Awesome. Well, it looks like that's a wrap. I want to thank our wonderful speaker for giving this awesome presentation, and I want to thank all the attendees for asking all these questions and participating. If Michael could send me the slides. I will try my best to post the slides on the Discord channel so you can go through them and look at them if you want to review any parts of the talk. Thank you, everybody. This was awesome. So glad we could have it. Bye.
Bye.